I will introduce Professor Oliver Schulte from Simon Fraser in Canada. I met Professor Schulte some years ago, first time actually in 2018. He had written quite a lot of hockey analytics papers already, and I wrote those. Actually, most of our own work was based on his work. And in 2018, he presented one of his works at ICHCAI, which is the main conference in artificial intelligence. It happened to be in Stockholm. I actually went up to Stockholm to visit him, and we had a nice chat together. I think it's really great that a person can present hockey analytics papers at this major conference in artificial intelligence, machine learning, data mining. But actually, his own best claim to fame, according to himself, is that he actually had a draw in chess against Kasparov.
Impressive.
It is impressive. So let's hear from this impressive guy and a talk about valuing actions and ranking hockey players with machine learning.
Good afternoon, and thank you for attending my presentation. I'm Oliver Schulte from Computing Science at Simon Fraser University in Vancouver, Canada. You see our campus location in the background behind me. I'd like to thank the organizers for all the work they've done in putting together a great conference and for giving me the opportunity to tell you about some of my work on machine learning and sports analytics. Two topics I'd like to discuss in some detail are action values and player ranking. So here's an outline of the talk. I would like to first introduce the concept of a success probability and explain why I think it is a fundamental problem in sports analytics. Then I would like to talk about action values and how you can derive them from success probabilities. Okay. The next topic is player ranking and how you can derive player rankings from action values. And then I would like to go into some detail on machine learning methods for estimating success probabilities. So what do I mean by success probability? Well, first, what do I mean by success? So for the purposes of this talk, I'm referring to a binary outcome that a team wants to bring about. The models I will be presenting are actually very flexible, and success can be defined according to the interest of the analyst or the coach. So just to give some examples, winning the game is obviously a type of success. Scoring a goal, also obvious. Within that, you can define some variants. For example, you can ask, are we going to score a goal within the next 2 minutes? One concept that I've worked with a lot is scoring the next goal. So is a team going to score the next goal regardless of how long in the future that might be? But you can have perhaps less obvious notions. So you could say, well, maybe I'm particularly interested in my team's ability to have the opponents draw penalties. Right? Or maybe I care about zone entries. We have a talk, this conference on zone entries, and maybe what I want to know is how good my team is at getting from the neutral zone into the offensive zone. Okay, so all this can be accommodated. Success probabilities are a dynamic quantity. That is, for every point in time in a match, we can estimate the probability that a team will succeed in the future. So I'm giving a familiar example, in-game win probabilities. Pettigrew in 2015 developed a win probability model for the NHL. And here is an illustration of what it looks like for a particular game, Philadelphia against Dallas. So you can see that at every point, like for example here, Philadelphia is ahead 2-1, and the model says, well, they have a 70% chance of winning, but then Dallas scores, and the chance drops, that Philadelphia wins drops below 50%. Okay, so at every point in time, we can assess a win probability. notice also that the win probabilities don't really change very much locally. You know, it's mainly goals that move them, right? And that's because winning is, for most points in the game, winning is a far away outcome. So as I mentioned in our work, we've used instead next goal probabilities, which are more sensitive to local actions. So here's another example of a success probability ticker. This time Penguins against Blue Jackets. For each team, we plot a curve showing the chance of scoring the next goal. And here you see, for example, the Penguins are on the attack. They have a quite high chance of scoring the next goal, but the Blue Jackets defend, so the chance goes back to something like 50%. Then again, Penguins are attacking, defending, attacking, and now they're launching a very dangerous attack. The chance of scoring the next goal goes very high. Defended, but you know, they keep pushing, and the model's getting very excited, and then the Penguins score. So one more example. So I know this is soccer. I hope I can be forgiven for showing something other than hockey, but this is from Luke Bourne's group, and he made a very nice visualization. Also, it's worth noting that a lot of these techniques can actually be transferred, certainly between continuous flow type games. So let's see. So here I will just run this. On the left, you see broadcast video. On the right, you see XY data, so tracking data. So Luke Bourne's model is based on tracking data. And then here at the bottom, you see another success value ticker, this time measuring the probability of finishing the possession with a goal, or more precisely, the difference between those probabilities for the teams. So I let this run through. Let me maybe run it one more time. And so what you can see, okay, oh, and it's Madrid playing against Barcelona, the Clásico. Okay, and now Barcelona gets the ball, but they're under pressure, and now backward pass here, and they're releasing the pressure, so that chances of scoring go up. And then there's another major event with another backward pass to Messi, who's very dangerous. Okay? And so you can see the model is picking up kind of intuitive major events. Okay? And at every point in the game, the model is watching what is happening and outputting a success probability. Okay, so next I want to talk about how we can use success probabilities to define action values. And the basic idea is to take the probability of success before an action, after an action, and look at whether the action increased this success probability and by how much. So if you think, if you go back to our success probability ticker, for example, the action that took us from around here to up here, that would have been a high impact action and would have gotten a lot of credit in this metric. So the Harvard Sports Analytics Group developed this idea for basketball 2014 at Sloan, and they said, we assert that most questions that coaches, players, and fans have about basketball can be phrased and answered in terms of expected future success. So, so my research has been about developing this idea for hockey. I also think that a lot of questions can be answered in this way. Be happy to discuss. Why do I think that, and what are the advantages of success probabilities? I think there's at least three major features. So one is the look ahead, right? We're talking about future success. So the success probability models are always looking ahead to the medium-term consequences of an action. Okay, and that's what we need. So a pass, right? Is it going to lead to an assist, which is going to lead to a shot, which is going to lead to a goal? So the pass itself may not have looked that valuable, but if it's likely to lead to success, it will be assigned a high value in these models. The second aspect is context awareness. All these models take as input the match context. Okay, so not all shots are equal, not all passes are equal. It's always dependent on context. It's important to distinguish achieving a high probability of success versus actual success, right? So really all you can ask a team to do is to get into a promising scoring situation. Whether or not they actually score also depends on how well the other team defends, and they may not control that. I think that point has become quite widely accepted in sports analytics also, thanks to the introduction of expected goal metrics. Another advantage is that all actions are evaluated on the same scale, namely differences in probabilities, right? So you don't have to think about, oh, are 3 zone entries as valuable as achieving 1 shot? For example, do you need somehow converting between the values for different actions, right? Everything is measured and comparable, apples to apples. So I wanted to make this a bit more concrete to show you what the distribution of action value looks like for the NHL. So this is from a model we built in 2014. And it's a box plot. So for every action, you see the distribution of impact values. So every point basically corresponds to a match context. And we're saying in that context, what was the impact of that action? And as you can see, for every action, there is quite a wide range of possible impact values depending on the match context. We can still look at the trends. So if we look at the averages, which are the lines in the box plots, right? So on average, shot has the highest positive impact, penalties have the highest negative impact. So that makes sense. Takeaways are actually very important. And especially depending on the match context, they can be really important, even more than shots. So that's quite interesting, but makes sense as well. Right, and we see that, for example, face-offs in the offensive zone are more important than face-offs in the neutral zone, so that makes sense. And again, everything's measured on the same scale, so we can talk about how important takeaways are on average compared to how important offensive zone face-offs are on average. So once we have action values, how can we use them to rank players? And the basic idea is to say, well, now we have a way to say how important was the action that this player performed at this time in this context, and we can just add that up for a given player. Okay? So we call that the goal impact metric, and because they're impacting the chances of scoring the next goal. Here's a result from a model we built for the 2013-14 NHL season. So a few things to highlight. Goal impact generally correlates with points, but it's not the same. For example, Sidney Crosby was like the points king, but Jason Spezza actually gets rated more highly. And you can sort of see why, because his plus minus is actually atrocious. And that's because he was playing for a poor team, the Senators. Okay, they're not a poor team always. In that season, they were a poor team. And so that shows you that this metric can distinguish between the individual contributions of someone like Jason Spezza, which were great, versus what the final outcomes were, which were not so great because of his teammates. And some evidence that we were right about this is we actually noticed that after we did this analysis, he requested a transfer to another team for that season. So again, it's probably a long, complex story, but it's consistent, at least with what we're finding. Here's another model and ranking we did for 2015-16. Here I'd like to highlight that you can compare our rankings with salaries, and you can use that to find players who should arguably have a higher salary. And again, in hindsight, we felt we were confirmed because both Gaudreau and Scheifele got a big increase in the next year. Another observation that I think is interesting in player salary is that our metric gives you an early signal. So what do I mean by that? So let's say you take 2015-16 data, you make a metric based on that, and you plot that against the amount of contract, okay, and it correlates fairly well, although certainly noisy. And so undervalued players will be kind of in the bottom right here, right? They will have a high metric value, but relatively low salary. And the percentage of undervalued players decreases from 16-17 to 17-18. Okay, so it's like if you look at what we are saying in 2015-16, then 2 years later, the teams agree even more. Okay, now again, this NHL salaries are a complicated story. So this is not like decisive evidence, but it's suggestive that you could use these metrics to as early signals for future success. One issue is with player ranking, you don't have ground truths. So how do you know that you're right? Well, we did like an eye test, as I've been showing you. Another thing we did is we looked at standard stats like goals, assists, face-offs won, and we reasoned, well, these stats are important, otherwise they wouldn't be recording them. And you want something like reasonably high correlation with what we know people care about. And then at the bottom 4 rows here, these are success probability values. We have expected goals here. And then these are built on the 3 bottoms are different versions of our models. And the success probability approach gives you generally the highest correlations. For example, with points, sort of our latest and greatest metric has 0.93 correlation. So I think we're in a good place here where, you know, we have a reasonable correlation with what we know is important in hockey, but it's still not the same, right? If we had 100% correlation with points, then you just use points. So we're adding information. Okay. Another thing you can do is drill down on player strengths. So one of the things that I've been very interested in is understanding the strengths and weaknesses of players. Like not just saying, oh, this is a great player overall, but why are they great? Where are they great? And again, always dependent on context. So because our model is already very context aware, that is easy to do. So here's an example. We discretized the rink in this work, and you can now say, okay, given the context of this being in this region and performing a pass reception, so receiving the puck from a pass, who achieves the highest impact receptions, and basically, if we look in this region here, where we're saying Erik Karlsson manages high impact receptions 37% of the time in this area, and the average player manages them 14% of the time. Also shows you how Erik Karlsson is a very offensively oriented defenseman, right? Playing towards the opposing goal shown here on the right. Yeah, so you can be very precise, right? Here, he's very good in this region. If you pass to him here, that's going to be a promising way to start an attack. Okay, so I hope I've shown you some applications of success probability models. I wanted to give some guidance now how you could build these things, right? Assuming you're like, oh, I want to do this myself. How do I do it? And want to discuss, at least give you some idea of how we've been doing it. That's really mainly what my research has focused on. Okay, so generally we have a machine learning approach. So what does that mean? Oh, sorry. So at the high level, at deployment time, it looks like this. Suppose you've built a classifier, a prediction system. You have a given match context at a given time. You convert that match context into a context feature vector, which summarizes the context. You feed that to the classifier, and then the classifier outputs a success probability. To learn or train the classifier, right, we have observed successes and failures. So in hindsight, we know whether a given possession ended in a goal or not. We have observed match contexts from our data. Okay? So that means we have both true labels that we want to predict, namely the actual success, and we have input features representing the context. Okay? And then we feed this data to a machine learning system, and the machine learning system then builds a classifier. Okay, in this talk, I'll be focusing on event data, also known as play-by-play data. So just an example here so that we're all on the same page. You can get this from nhl.com. So you see here, you get information about what happened. It was a face-off, who was involved in the face-off, where was the face-off located, what time did it happen. If you want to visualize the dynamics of this, here's a little animation, right? So you can think of the puck as moving around on the rink from state to state. And every action is influencing what the next state is. Okay, so let me maybe run that one more time. So here we have a loose puck recovery, moves the puck towards the opposing goal as a check, moves it away. And then we get to a pass and a reception, which starts sort of the counterattack, ending in a carry. So technically, we can think of this as a Markov decision process. So a Markov process is a dynamic process that moves from state to state with a certain probability. And it's a Markov decision process because we have actions that intervene to change the state transition probabilities. Okay, don't worry if that didn't make sense. I just wanted to kind of drop that keyword, Markov decision process. Okay, so if we have our event data, we need to now specify our ground truth success labels. And we can do that by first defining our notion of success and then annotating the data with another column. And as I mentioned, you can define success in different ways, but the machine learning system doesn't actually matter, doesn't care about that. You just say, okay, here's what I want you to predict. So here you see an example. If we take the notion of success being next goal, we have play-by-play data. In fact, team 16 scores the next goal. And so then when team 15 is acting, we put y equals 0, right? Because they did not score the next goal. Then at the next step, y equals 0. And then when team 16 acts, we say y equals 1 because they do score the next goal, right? And so on. Context, as I said, can be represented as a feature vector. That's fairly easy to see if you have things like score differential, manpower differential. You can just list those. The tricky question is what to do about the previous match history. And a simple approach that I'm kind of recommending for a basic model is to fix a sliding window size. So common value would be 3. This is what the Cruise et al. Used in soccer. 4, this is what DeepMind uses in video games. 10 is what we have used in our hockey analysis, but that's probably very, very big, maybe too complicated for a basic model. And then you just say, oh, I have my previous, say, 3 events, and I use that as the context for the current event. Okay, so let me just illustrate that. So suppose we choose our window of size 2, right? So then we would say the context for the last event at the bottom includes the previous event and the event before that. So these two. The context for this event here, third row from the bottom, includes the previous row and the row before that. Okay, so this way we can still have a finite vector representing the context. Let me just sort of trace that out for you. So for example, if we have two features, manpower differential and the action taken, and we have play-by-play data that look like this. So then in the last row, we have manpower even and goal. So we can call those time 0. And then we can say one previous time step. So action -1 was pass. Let's see how this comes here. Manpower at time -1 was even. Okay. And then we go one more row back. And we have the action versus turnover at time -2, and manpower was even at -2. Okay, so to put the data into this form, you need to do some data pre-processing. We've written a script to do it. You know, it's some extra work, but it's fairly straightforward to program. And once you have the data in this form, you can run any standard classifier. Okay, because now you just, from the classifier's point of view, you just have a bunch of rows with the inputs. So here we would have 2, 4, 6 input in this example, and 1 output value that you're trying to predict. And if you come from statistics, you might like logistic regression, machine learning. People often use gradient boosted decision trees, very powerful model. I like logistic model trees, also quite powerful, but interpretable. And just to give you an excerpt from a tree, just to give you a sense of what such a model might look like. So our model tree says, okay, first thing I want to know is whether the away team has possession or not. Okay, and I'm trying to predict the probability that the home team scores the next goal. So if the away team has possession, then the probability that the home team scores the next goal goes fairly low, 0.39, right? Because they don't have possession. If the home team has possession, then the model wants to know how much time is left in the game. And basically that's because if there's not much time left, then there isn't much time left to score. And if there is, you know, if we're not near the end, so no means not being near the end, then the model wants to know, okay, does the home team have a manpower advantage or not, right? And that also makes sense because, you know, one of the first questions you want to ask is, are they on a power play? Then their chances are higher to score. Right, so that's the sort of thing you can learn automatically once you've done this pre-processing. An alternative would be to use a recurrent neural network. Also long short-term memory, that's what we used in our work. An advantage is that it's built to handle sequence data, so you don't need to do any of this sliding window pre-processing. You may find that less familiar than things, say something like logistic regression or classifiers. Also, the results can be more difficult to interpret. It's just a black box, so you cannot trace through the reasoning of the model like I was just doing. You just get some number, that's the output. If that is an issue with deep learning, I want to mention mimic learning. I think is a nice approach, and we've written a few papers on how to use it in sports analytics. And the basic idea is you train a neural network to give you accurate predictions, and then you train a tree model to mimic the neural network. Okay, so the tree model isn't trying to predict the actual success, it's trying to predict what the neural network thinks the success probability is. Okay, so you get the accuracy of the neural network, and you get the interpretability of a tree model. Just want to mention it, this idea of mimic learning has been around since the 90s in machine learning, but I've found that not everyone in sports analytics has heard of it, but often people really like it. Okay, so then the last topic is reinforcement learning as an alternative to this classifier approach. And I just want to describe it as a high level to give you an idea of what it is. This is really what I focused on, so I have lots of papers with more details. This is basically kind of a advertisement to encourage you to look at reinforcement learning. It's the branch of machine learning that studies learning to act. It's been around a long time, many ideas, powerful algorithms, a lot actually that we can take off the shelf for sports analytics or adapt at least. And it's a very good match with what I've been discussing, because learning success probabilities is one of the fundamental problems in RL. They call it learning a value function. I actually think that sports analytics ought to be viewed as a subset of RL, one of the major application areas. Okay, there's a great online introduction if you want to learn more about it, and many many tutorials and videos. So how is that different from the classifier approach I've been discussing? Well, the classifier approach really implicitly, it says all success probabilities are independent. Okay, so once you've made your table and you list every event and the context feature and the observed success, the classifier just predicts all the success probabilities independently. So that completely ignores the temporal dynamics and the fact that success chances are highly correlated. So if you're in a very promising situation now, likely you have a high chance of scoring 10 seconds later. So reinforcement learning takes the opposite approach, and they want to exploit these temporal connections. And the key concept here is the state transition probabilities. The first step is to model the chance of getting from one state to another. And so I will show you a demo. And apologies for this being basketball again. I just don't have such a nice visualization. And so here you see a basketball game. Every box is a player. Duncan has the ball. And what the model wants to predict is what's going to happen next. That is to say, where the ball is going to go. So Duncan could most likely, according to the model, he will pass to Parker. Okay, this is the big line. But this is interactive. So for example, if we move Duncan right in front of the goal, then, sorry, the basket, then Duncan is most likely to take a shot. Okay, so state transition probabilities answer the question of what is likely to happen next. In our NHL models, we built a big state space with a rich set of context, 1.3 million states. We estimated state transition probabilities for all of them. Okay? And then once you have state transition probabilities, you can predict future success using a famous efficient algorithm called dynamic programming. And I just like to show the basic idea. So suppose you have your one-step transition probabilities, okay, like I was showing you in the basketball demo, and then you can extend that to any number of steps as follows. So suppose I want to get from S0 to S1, let's say in 2 steps. So then I can get from S0 to S0, so state 0, and then from state 0 to state 1. Okay, so that would be one pass, one two-step pass. And I can then compute the probability of this path occurring. That would be 0.1 times 0.2. Okay, and I have 3 possible paths, right, for getting from S0 to S1 of length 2. For each of these, I can compute the probability and add them up. Okay, so that's the basic idea. And the observation is that this works even for any lengths. If I use the one-step probabilities at the top level, and then the L-step probabilities at the bottom level. So for example, suppose that I've already computed the probability of getting from S0 to S1 in 3 steps. Okay? Then I can use this computation to get the probability of getting from S0 to S1 in 4 steps. Okay, very beautiful, very powerful idea. Okay, and so if we want now all the success probabilities, we can do this by increasing the look ahead. So we start with look ahead equals 1. Okay, what's my chance of, say, scoring a goal in 1 step? Okay, and then I can compute that using the state transition probabilities. And then I increase the look ahead 2, 3, 4, and at every point I update my estimates of what's the chance of getting to getting to success. And for example, in our NHL models, we found that you need 13 steps look ahead. And after that, your success estimates don't really change anymore, okay? Which makes sense. So if I tell you now, what's the chance, given the match context, that the team is going to score in 13 steps or in 14 steps, it's going to start to be very similar because the extra look ahead doesn't really change the probabilities anymore. So I just have a visualization again from soccer. This has become somewhat popular under the heading of X threat, expected threat. I haven't seen this developed in hockey. Okay, if you look at this post, they have the formulas and everything. But let's just sort of trace it through. So here you are trying to score a goal. At iteration 0, you're saying, well, what's the chance of scoring in 0 steps? Well, that's 0 because, right, I need at least 1 step to score. So this is all flat. When I go to iteration 1, now I can say, oh, if I'm here, I have a 39.3% chance of scoring with a ball. I can go here, 14.1 and 1 chance because I'm further away, right? So this is saying, basically this is saying if I take a shot now, what's the chance of scoring? Now I can go away 2 iterations of this. So look ahead 2. And now you can see I start to get an idea of the dynamics. So, right, for example, here I might make a pass and then score, right? Because I'm looking, so further look ahead, then I can go to look ahead 3, and I update my probabilities, right, of scoring within 3 actions, okay? And so forth. Eventually I get to 5, and with 5 actions, I can even get non-zero probabilities fairly far away from the goal. Okay, so let me summarize this and also give you an overview. So if you have continuous data like we do in hockey, first you have to decide whether you want to discretize, say the rink, especially. If you're willing to do that, and I've shown you some examples of where we did do it, then you can apply dynamic programming, this iterative look ahead idea. Okay, and I've given you some references, sort of models you could follow. If you don't want to discretize and just use spatial and temporal coordinates as they are, then you could use a classifier. You could use reinforcement learning. If you use the classifier, you can use the sliding window technique. De Cruz et al. Is a nice reference where they do this in detail for soccer. You can also use reinforcement learning techniques, not based on dynamic programming and transition probabilities. These are so-called model-free techniques using something called temporal difference learning. So I can explain the high-level idea if you like, but for now I'm just dropping those keywords. And again, we have a few papers on hockey where we show how you can apply temporal difference learning. So the big advantage of that is that basically no pre-processing, no discretization. You can just use the data as they are. And there are packages that include that, and we've posted our own code, but it's a kind of an advanced topic. So then I'd like to mention some extensions of this basic setup that I've worked on, or in the past, or hopefully in the future. Adding to the context the player identities, who is acting, is an important topic, right? Because it makes a difference who is taking a shot, who is passing. And we've developed a model that can capture a lot of the differences between players, their styles, their strengths and weaknesses through what's called a player embedding, where we assign them a kind of soft cluster or a latent vector. And yeah, that's quite a sophisticated model, and it seems to work very well. So I'm proud of that work. It also makes sense to evaluate at higher levels than players. In hockey, for example, evaluating lines would be very natural. There's a nice paper by Jung et al. Here from LINHAC on evaluating pairs of players. So instead of defining success explicitly by the analyst, you could also try to infer the objectives of the team, like what is it that they're trying to get to, right? Are they trying to get into the offensive zone? Are they trying to get into the slot? Are they trying to go for the left, the right? So there's an area called inverse reinforcement learning that tries to do that, to infer the objectives of agents. So we published a paper. I think that's a rich area. And one of the things I'm thinking about these days is to determine what the optimal actions are for a given match context. So can we figure out, recommend what a player ought to do in this situation? Okay, so let me conclude. So I think estimating success probability is really a fundamental problem in hockey analytics, meaning that if we solve that, we can solve many other problems. Machine learning models can include rich match contexts to provide what useful success probabilities. I hope I've shown you enough to you can see it's useful. And basically you can start with some basic classifier type, and then if you're getting interesting results, if you want to handle more complex phenomena or increase the accuracy, then you can go to reinforcement learning, deep reinforcement learning. So there's a lot of tools you can draw on. Yeah, and reinforcement learning, I think, is especially suitable for complex dynamic domains. So thank you very much for your attention. I'd like to acknowledge my collaborators, and I'm happy to have a discussion now.
Professor Schultz, that was certainly phenomenal. We have a short time here, so I have one question for you. You talked about goal impact metrics. You then compare that in the same schedule or with Jason Spezza. You had actual points and actual plus minus. The goal impact metrics, how do we need to understand that so we can actually use that in the hockey world?
Oh, well, the intuition is that it measures how much difference a player's action makes to your team's chances of scoring. And so it actually can also be thought of as a replacement. So if you were to replace the player by an average player, how much better or worse would you do in terms of the goals that you can expect to get? Does that help?
When you use that, then you're obviously putting a lot on the coaching staff to try to understand that. As again, points are very simply goals and assists, and plus minus are plus minus. And then you're putting into this third goals impact metrics is something that they need to learn an awful lot about to use that in their analysis.
Right. Yeah, I think so. The metric as a whole is not so. It's not nowhere as simple to explain as plus minus, for example. That's why I showed the example of the drill down. I think what you'd want to do is make it specific to a context. So with Carlson, I was saying, well, when you're in this region, he manages to perform the reception of the action. So he's very good in a specific region with a specific action. So I think to make it actionable for coaches, you want to drill down and get, extract from it where the player specifically is stronger or weaker. So.
Professor Schulte, thank you so much for your time. Great presentation, and thank you for being with us and participating.
Okay, thanks for the question.